So we're finishing up chapter 6, and our last topic is circular motion, which we've already touched on a little bit already because we've already studied centripetal acceleration. But if there's an acceleration, it must be coming from a force. So centripetal force is simply the name of the force, or maybe it's more than one force. Maybe it's a net force, maybe it's a combination of something that keeps objects moving in a circle. And if it would also be directed towards the center of the circle. Some misconceptions that I see all the time, again, centripetal force is not an extra force. It's a force we've already studied, but it's not like an extra force you would add into your free body diagram. It's just due to certain forces that are already there, like we'll show on the next slide. You may have heard the term centrifugal force before, but that's not a real physics term. It's just the feeling of circular motion. Because if you're driving your car, and let's say you take a sharp left-hand turn, what does it kind of feel like?
A right turn?
Yeah, it kind of feels like you're going to the right. Are you really going to the right? No, you're just trying to continue your natural straight line motion. I probably should have picked a right turn. So you make a right turn, you're still continuing your natural straight line motion, but what is it maybe that makes you turn? There's a couple things you could pick. Like if this wasn't there, you wouldn't turn with the car. Friction between your butt and the seat. I mean, you ever seen the people with Jeeps and there's no door on the side at all? Okay, well, hopefully they're not sitting on frictionless seats. I mentioned the door. So maybe if you're taking a fast enough turn, you get pushed into the door. So there's a push force or a normal force from the door. And what else, hopefully, do we have on? Our seatbelt. Maybe there's some tension in the seatbelt keeping us moving in a circle. So same formula, F equals ma. Do you remember our centripetal acceleration formula?
AC equals 2 pi r over velocity.
2 pi r, no.
No, maybe.
It's not it's not circumference over velocity, or the
What is it?
circumference over the
No. Tyler? V squared over r. Okay, now if we knew the period of something, we did have velocity formulas there, but.
Why does it matter if it's left or right?
Well, if it's a left turn, it's less likely that the door is going to push on you. You're right, it doesn't really matter. Yeah. Unless we're in Europe or something. So what forces are actually acting on you? This is what we just talked about.
Passenger seat, so it would be the door in the left-hand turn.
Is that out there?
Yeah.
Oh, okay. Tension in seatbelt, friction with seat. What was the other? Oh, a normal force from door. So these combined, the center-seeking components of these forces would be the centripetal force. Okay. So again, to think about the centripetal force, think without this force, if it is just one, this object wouldn't keep a circular path. So what force is it that's helping the object keep a circular path? Well, how about this example, ball swung in a circle by a string. Without the what? The ball would not move in a circle. Yeah, without the string. So tension here would be the centripetal force. It's not some extra force, just the centripetal force is the tension. All right, some other examples. A car making a turn. Speaking of the car, not the person in the car, what is the force that would allow a car to make a turn? Friction. Without friction, you could turn your tires, but you're not necessarily going to make a turn. Force friction. All right, person in a car making a turn, we just did this one. Friction with seat, normal force with door, maybe tension in a seatbelt. All of those together could be the centripetal force. Yo-yo doing around the world. I can actually do that. Tension of the string. Without the string, you are just throwing a yo-yo. Ooh, person in a gravitron. You know what that is?
It's the thing that spins you around and around and around and around and around.
Yeah, and you're like stuck to the side. One of those fair rides.
Yeah. So then the close to that.
Are we going to Carolina?
Here's you. I think Mr. Mary is trying to organize that field trip.
I was sad. I didn't get to Carolina much. Yeah, we made it.
Yes, I think Mr. Merritt's organizing that for this year. All right, there's you stuck in the gravitron. What are the forces acting on you?
The back thing pushing you forward.
Okay, there's a normal force coming.
So you're not flying out.
That, by the way, well, not the circle. Have you ever seen this notation for vectors?
No.
Do you remember what it meant?
Yes. It's going around your hand. Or if you were holding it.
Like the right hand rule. It's a way of saying coming out of your paper. You know, it is supposed to just represent an arrow, but three-dimensionally. So if I just put a dot,
That means
not that we ever really do that for mechanics, but
that
We
means
did a
it's
whole
going
test on that.
this way instead of
yeah, that's well, it's more for electricity than the right-hand rule. But anyway, we have the normal force from the surface pushing on the guy outward, I guess. So what else? I can't really draw that three-dimensionally. We'll say that way.
So he's like up against the
He's like
wall.
this, yeah.
Oh, okay.
Okay, so what else? Friction, which way?
There's really no way to be higher.
Let's say friction for a second. What else is always there?
Gravity.
Force of gravity, the guy's weight.
So if a weight, wouldn't that have to be an opposite?
So when you're in the gravitron, you know, you're in this like circular room, you're standing next to the wall, they start spinning it, and then the floor drops out from under you, and you're just stuck there on the wall, spinning. So your weight's pulling you down, but if you're not going down, it must be because of friction supporting your weight. So if you did this in like an icy wall or something, you're wearing your Teflon suit, you probably would still fall down. Which means our centripetal force, the force that is keeping us in circular motion, must be which one of these three? The normal. The normal is the center-seeking force, which sort of makes sense. I mean, without the wall, you obviously wouldn't be moving in a circle. All right, and then the moon orbiting the Earth. Good. Force of gravity. I just want us to skip to these real quick since the rest were just problems. Your natural forces, you might have one conceptual question sort of on these. You've got, so natural forces mean they're field forces, there's no contact needed. It's not like I'm pushing on you because I'm touching you. But the gravitational force, like the Earth's pulling on me without me actually touching the Earth. All right, that's one of our natural forces. Electricity and magnetism are sort of combined. You know, the pull of magnets, that's natural. You don't have to touch the magnets together to feel that. And then inside the nucleus, we have the strong nuclear and weak nuclear forces, varying in strength and, you know, of course, acting over different distances. These two, of course, are strong, but act over incredibly small distances just in the nucleus. Okay, so back to the conical pendulum. Okay, so this is just a pendulum, which is interesting. It would, you know, keep moving back and forth in the same plane, regardless. Darn, not coordinated. Regardless of how I move this pivot up here, an example of this is at Clemson University, Foucault pendulum. And if you go back and look at it during different times of the day, it looks as though it has moved. It looks like it's doing that, or maybe later it's doing this, but it's not. It's just moving the same plane with the Earth spinning underneath it, which is kind of neat. Anyway, a conical pendulum would be if I did like this. Just, making a cone. Okay. All right, so we have our conical pendulum, and these will all be pretty much constant speed examples. There is still an acceleration because we're changing direction. It's not constant velocity because direction's changing, but we will keep constant velocity or constant speeds. So sweeping out a circle, mass m, string length L, the object revolves at constant speed in a horizontal circle of radius r, as shown below. Find an expression for v simply in terms of these three variables. So L, theta, and g, which means tension or mass or radius I really do not want to be involved in my answer. So when you got a question like that, kind of just start writing down everything you know. This is Tyler just answered this for us. What's really the only helpful equation we know that's got velocity in it? Or really, I should say speed. And what does that equal? Let's try in a color. Okay, so I probably need some information relating to the centripetal acceleration and the radius. If I wanted to stick an m on there, it's in the notes. I can stick an m on both sides, and what if I simply made the left-hand side? Yeah, net force. And this is specifically centripetal acceleration, so this would be the net force, leading to centripetal acceleration. But anyway, so the net force equals mv squared over r. Should make sense, just m times a.
So did you just add mass?
Yeah, I just put mass in on both sides. Because I know I'm going to be dealing with forces, so it sort of makes sense to pull in a force. Again, the goal is to solve for v. And I only wanted it in terms of L, theta, and g. So let's at least start with the net force. What is the net force due to? What's the centripetal force? What is the center-seeking force in this problem? More specific. Tension. Yes. Okay, so I do have tension, pulling on this object, and it would have components. And specifically, the x component here is the center-seeking component. So that's going to be my centripetal force right there. So now I'd like some relationship for Tx. So I can say all of this equals Tx, because that is the centripetal force. Okay, but what is Tx equal to?
The sine of theta times t.
Very good. Okay, so that helps a little bit. I've gotten rid of the x part. Theta I did want involved in my answer, so it's good to see theta there. But tension I really didn't want involved in my answer, so is there any other expression I know that would be true that involves t?
Mass on the acceleration. Force.
Well, the t, that's what we're saying, but just for tx.
Okay.
But I can also look at ty. What does it equal?
But that also must be the total mass times mass.
Good. Okay, so the y component will be the cosine, and that should equal mass times gravity because this object is not, moving up or down. It's staying in this same plane. Okay, so hopefully I can use that to get rid of the t. Okay, so t, good, equals mass times gravity divided by cosine. And I'm going to plug that in here for tx, and we're going to rewrite at the top. That's tx.
What did that MGTN equate?
Yes. Good. Notice you can simplify that. And what happens to the m's anyway?
They cancel.
Good. We've got m's on both sides. That's helpful. That will cancel out.
We just have to get rid of the
Yeah. So that's good, but it's not following my directions yet. And I do want to square root it, but I also, and I could do that now, but I want to get rid of this r. It did not say in terms of r, it said in terms of L. So what's the relationship between L and R? That really is just a geometric relationship. It's not a force relationship. I mean, I made this triangle for the tension components, but I could have just as easily
made it for the on.
had the L on the side and the R on the bottom.
So that means L sine. Yeah, L sine.
Good. So I can plug that in. I was really trying to work on my space management. So we got LG, and we do have a sine and a tangent, really no way to simplify that. And we square root it all. And that is a conical pendulum formula that would, of course, apply in this situation, where you had constant speed, string length L, gravity, et cetera, et cetera. Okay, banked turn. This is a common problem. You think of like NASCAR. They're not just going around in a flat track. The turns are banked. Often the whole track is banked. Why? To help in addition to friction. Friction is keeping them in the circle, but I could also get some amount of normal force pushing towards the center of the circle if you banked the track. So this says a civil engineer wishes to design a curved banked exit ramp. And you'll see that phrase a few times. If your exit ramp is designed, it's designed in such a way that a car will not have to rely on friction around the curve without skidding. That's why your speed limits are always really low for the exits. But the theory is, if it was all iced over and you were going that speed limit, you wouldn't fly off the road.
Do we ever break the normal force down into components?
We're about to. Yeah, we can break anything down into components just depending on whichever way we want to tilt our x and y axis. And I'll explain why I want to do it this way for this problem. Okay, so let's say the designed speed for the ramp is 13.4 meters per second, about 30 miles an hour. And the radius of the curve, which I know they're not all complete circles, but you could still imagine part of it as a section of a curve, is 50 meters. At what angle should the car be banked? So I want to find the bank angle. Now, usually we find components of weight, but we're not going to do that this time because we're going to imagine this as like a bird's eye view, and I want the center-seeking components of forces, that would be my centripetal forces. So if this is a non-friction related problem, there is no friction. The only center-seeking force would be the normal force. But not the normal force entirely, just the component of it that's pointing in towards the center of the circle. Not down at the ground like that, not angled down, but horizontally in towards the center of the circle. So in this case, we do want to break down the normal force into components. And it says it doesn't have to rely on friction, so we're going to actually ignore friction. But something you need to consider for other problems would be, if this car was going too fast, which way would friction be acting? Your choices being, of course, either down the incline or up the incline. And I guess the question would be, if this car is going too fast, what's its tendency to fly up off the incline or just spiral down in? Yeah, go flying off straight and out. So if the tendency, if it's going too fast, would be to go out of the curve, friction would be acting which way? If you're going too fast, good, down. So that's the too fast example. Of course, if you're going too slow and it's really icy, the car would just kind of slide down in and friction would be acting the other way. But anyway, I'm going to finish. It's going to be a lightning fast problem. All right, you were again given the velocity, so you're thinking of our new equation. Interesting thing here is, again, mass will not matter. And it shouldn't matter. It shouldn't matter if you're an 18-wheeler on an exit ramp or a small convertible. And looking at our free body diagram, which has kind of been drawn for us, there's our normal force, there's our weight. Come up with the x and y components of normal force, which is new to us. You know, we would break it down into cosine and sine, this being the angle here. Okay, so our net force is specifically due to normal x, so that's going to be n sine of theta. And I don't know what n is, but what's another equation that would be true relating n? Equals? Yeah, the ups equal the downs equals mg. So n would be mg over cosine, plug in over here. And of course we end up with sine over cosine again, which is what? Tangent. M's cancel.
And what were we looking for again?
Theta.
Theta. 10 to the negative 1 of that.
And v squared was given, I think it was like 13. Oh, I lost it.
That was a G by the symbol.
What's the radius, 50 meters? Oh, I needed a very fast calculator person. But this is also just a kind of a good equation to know. Wait, we got it. This is without friction, though. So we had made it all the way through this problem, and we had ended up with this equation, which is useful to just memorize, so you can save yourself some time in deriving it. But again, what the whole point of this equation was we were finding the angle we would need to bank our exit ramp so that somebody could, exit off the highway without sliding, without flying off the curve because they were going, or because it was like icy or something. So it's the angle that would keep somebody in a turn without friction. So they did not have to rely on friction. So if you were ever asked to find that angle that the exit ramp's sort of designed for without friction to keep somebody in that turn, this is the equation you would want. Now, we also did discuss briefly what would happen if friction was present, which way would it act? And that does depend on your speed, okay? Because if obviously you're moving really fast, you're going to need a stronger centripetal force to keep you moving in your circle. So if you're moving too fast, it's like this exit ramp's designed for maybe 30 miles an hour at this angle. If you're moving too fast, which way did friction act? Yeah, if you're moving too fast, you're going to fly off of it. So friction would act, yeah, the opposite way. Friction opposes motion. So if we're going too fast, friction's going to act, and it would be, parallel to the road. So it would act sort of inward, but at this angle. So you would maybe need to find components if they're asking you something about the center-seeking component or the centripetal force of it. And then if you're going too slow, then you just kind of be like spiraling inwards. So you'd be sliding in if you're going too slow, so friction would act the other way. All right, so that's what you need to know about the banked exit ramp problem. And our answer was 20 degrees when we finally plugged everything in.
The opposite of friction, when friction is pulling it down, is that centrifugal force? When it pushes, is that the opposite? The force opposing?
Like out?
Yeah.
It's just the feeling of being thrown out. It's not an actual force. It's just the feeling of being pushed out of the circle. Like we said, okay, and so this car is kind of making a right-hand turn. So any person inside would want to be moving in a straight line. Natural motion is straight line motion. But they would feel like maybe they'd be pressed up against the seat. So they would feel the normal force from the seat. So that feeling they call the centrifugal force. But it's not like that person's actually being thrown out. There isn't one. It's a fictitious thing. It's a nonsense term. It's not a science term at all. So don't ever use that on your AP test. Okay. So that left us with the LoopDeloop. Diavolo. This was a real guy. Real LoopDeloop. I'm hoping for his safety this part of the track gets put in place before he makes it down there. But this is possible to do. Maybe this at the circus or something. Okay, so here's our problem with the LoopDeloop. So our 1901 circus performer, Allo Daredevil Diavolo, introduced the son of riding a bicycle in a LoopDeloop. Assuming the loop is a circle with a radius of 2.7 meters, what's the least speed? And that's usually how the question will be asked. The least speed he could have at the top of the loop if he's to remain in contact there. So we're talking about the top of the loop, and we'll, in the next couple slides, talk about other points in the loop and what might be true there. Well, I guess I could draw him. There's a little bicycle. He's upside down. So we're talking about speed. This is a circular motion problem. We're probably going to want that v squared over r for acceleration. But what is a centripetal force anyway? He's here at the top of the loop, right here, because this will change at different points. But right here, what forces are acting on him? Weight. Force down. And?
Normal force up.
Normal force up?
Well, he's like pushing.
Normal force down as well?
Normal force down.
Because it's pushing him back here.
Okay, because it's from the surface and he's like inside the loop, so it'll be pushing down. Now at the bottom, what way would the normal force be pushing? Up. Okay, but here's the thing about the normal force. If he's in contact with the loop, there would be a normal force. But the phrasing is, what's the least speed he needs to stay in contact with the loop? So if he were going any slower, what would the normal force equal? 0. So that's our assumption. We are assuming the normal force equals 0, or is about 2. Which means our centripetal force is just due to the what? There would be, you're right, there would be friction, if he's cycling around, actually opposing his tires, so it'd be that way. But as far as centripetal force, that's not center seeking. So which way, so what is the only centripetal force here? The weight. That is the only thing keeping me in the circle at that point. I realize that it changes a little bit as he moves around the circle, but right here, it's just the weight. So our centripetal force equals weight. Our centripetal force equals mass times, well, because weight equals mass times gravity, but keep going. Our centripetal force also equals, or just any net force equals mass times acceleration. But specifically to plug in our centripetal acceleration, we're going to plug in v squared over r. So interestingly, again, does it matter what this guy's mass is? No, it cancels. And hopefully it wouldn't matter if you threw in, a teenager who was not as heavy, or somebody who was heavier. Hopefully it wouldn't matter what their weight is. So that's pretty much it. Just solve for v. We're going to need the square root of g times r. And we got our radius is 2.7. So 5.15 meters per second, about 10 miles per hour. So doable. Okay, a couple other questions on the loop real quick. While we're thinking about it. All right, draw a free body diagram at each point of the loop-the-loop and label what the centripetal force is equal to. All right, so here's like a roller coaster loop-the-loop situation. I'm just going to put each spot, 1, 2, inside the track, like we're not on the outside of this. So, at spot 1, what forces do you have acting? Which way do they go?
Weight down.
Weight down. Normal up. I'm going to leave off friction because it's not center seeking. It's not in this line at all. But you're right, we could throw in friction. So what is the centripetal force right here? More than that. It's sort of like when I asked you to come up with the net force equations in that other sheet. Normal is certainly the center-seeking force here. Is there anything opposing the normal force? Normal minus weight. Okay, good. So normal minus weight right there. And sometimes in problems they will ask you, like for a loop-loop problem, what is your apparent weight? So of course your weight never changes, because your mass shouldn't be changing, gravity shouldn't be changing, but the normal force will, in order to keep a set certain velocity in this loop-loop, or set certain speed, I should say. So if they ask you for your apparent weight, that's going to be the normal force. That's going to be what you feel pushing against you. All right, spot number 2. Okay, spot 2. I just didn't want to compute. I should have left it the same color. Okay, what forces are acting here? Weight, of course, down. And normal in. Yeah, normal left. Now, is the normal force in spot number 2 going to be equal to the normal force in spot number 1 if this is keeping a set speed? No, because the normal force here has to be even bigger. Does that make sense? Because it's got to overcome the weight as well. It's got to overcome the weight and be a strong enough force to keep whatever speed you want for your roller coaster. So don't necessarily think that wherever you solve for the normal force is going to be the same value. So here our centripetal force is equal to what? Is there a weight x?
Or normal x.
Which is, yeah, along the x-axis. Is there a x component of weight here? No, just straight down, so that's it. Normal force would just be the centripetal force, that's it. All right, at the top, directions of forces. Weight down. And in this case, normal down. Now, if they give you the scenario where it's moving, just barely fast enough to stay in the loop, then normal would be nothing. But if they don't say that, then the centripetal force here is equal to what? Normal plus weight. And then if they don't say that the object in the loop-de-loop is going only fast enough to stay in the loop, like just barely fast enough to stay in the loop, then you would have to assume there is some normal force. All right, and of course, spot 4 is the same as spot 2. Okay, so once again, don't think that all the normal forces are the same. All these centripetal forces would be the same, but the normals aren't. Okay, so here's a problem based on what we were just sort of going over. The centripetal force is always equal to 1,000 newtons, and if it's consistent centripetal force, then you would have a consistent speed. What must be the apparent weight at each point on the track if the weight of the roller coaster is 400 newtons? I wonder if I could bring back what I just had. Yes. Okay, well, a little bit shifted, but you got the point there. All you got to do is just plug in to all those little equations that we just wrote. So the centripetal force is equal to 1,000. Well, plug in 1,000. So 1,000 equals, for this bottom case, normal minus 400. So the normal force would be 1,400 at the bottom. How about spot 2? Just 1,000. Normal force is equal to centripetal force. What about number 3, though?
600.
There you go. So where do you feel the heaviest on this roller coaster?
At the bottom.
At the bottom. Okay, so that is it for our circular notes. Now let's get our books out and try to quickly go through Chapter 5 discussion questions.